Where we stopped yesterday, I believe, was this here, 2, 4, 6. We're writing subsets. So that's what we're going to be picking up to start with. One thing I will say before we start with, in the grade book, I do have a slot for bonus points. So the trivia, math trivia each week, I put them in there. Any bonus, because I do simple point for calculating grades, all bonus are going to be out of 0 points. I have a feeling it comes up every year. I have a 0 on this assignment. I will say check and see how many points it's out of. Because 0 out of 0 does not count against you. Because if it's worth 0 points, it's not adding 0 to the overall points given out. So it's not actually hurting you. So when points get put in there, it attributes to your total points earned, not the total points given. So it actually puts your grade up. There will be makeup points, MUP, for tests. If you don't do the makeup points, it's going to be a 0 out of 0. So if your parents are asking, why do you have these zeros here? Check and see what it's out of first, because if it's out of 0 points, it's actually not hurting your grade. Does that kind of make sense? It does come up every year. Why do I have these zeros? That's why they're there. Okay? Now, subsets. A subset is part of the whole. It has every part all the way up to everything in the whole set. So we did a few of these yesterday with one. I know with A, B, 4, 5, we did these here. So we look at 2, 4, 6. I told you that there was 1, 2, 3, 4, 5, 6, 7 subsets for this year. Yes? Well, we know one of them is going to be what? 2. Just the set containing 2, because it's part of the whole. Our next one would be 4 and 6. Because we can have sets containing one element. 2, 4, 6 are all contained in the set 2, 4, 6, so we can have one of each. But we could also have groups of 2. So we could have 2, 4. Or 2, 6. Or 4, 6. And 2, 4, 6. So that there would be all the subsets, because a subset, everything in a set is contained in the other set. 2 is contained in 2, 4, 6, 4, 6, 2, 4, 2, 6, 4, 6, and 2, 4, 6. It can be everything. Questions on how we found these? Now, order does not matter. 2, 4, and 4, 2 will be the same set. For what we're doing, they are the exact same set. We're not going to be making it different. Are you ready for the next one? Kind of, sort of. I always start with ones. So for E, F, G, H, we have the set containing E, F, G, H. So we have a set just containing each single element. Each object is considered an element. All right, because that takes care of all of our individual just one element subsets. So we can look at 2, which would be EF, EG, EH. And I do like doing it this way. Just we start with that first letter and do every combination with it. EF, EG, EH. If there was one after H, we would do it and just kind of run through that list. But we don't have any more with E, so we can switch from E to F, and we'd have FG, and then FH. Do you have any more that we can do with F? So then we'd move on to what? G, and we'd have GH. Then we just follow through with that, but there's no other letters after H. So we've taken care of all the subsets that have just one element. Now we've taken care of all the subsets that have 2. So what can we do next? 3. E, F, G. E, F, H. Yes. We actually have one more set of 3. Because we did do E, F, G, E, F, H. I agree with GH. But our first letter would be E. And especially with the 3s, how I look at it to make sure we got them all, is I start with E for sure, second letter F. Because we can keep those 2 in place. And we get E, F, G. But we can keep E and F and go to H, E, F, H, E, F, K, E, F, L. And we keep going out from there until I can't go any further. Keep E the same. Let's move the next one, the F down one. So E, G, H. And then do reiterations with E and G. Till we can't anymore. But I think we got them all. E, F, G, E, F, H. F, G, H. Yes. E, F, G, H. I will tell you this, the way that, or order that you list all of these subsets does not matter. As long as you have them all. That's the thing that matters. Especially on the homework or the test where this shows up, you will see, especially when I hand it back, I will be putting check marks on them. All I'm doing is just going down the list and making sure they're all there. That's all I'm looking for. And hopefully you start seeing that these are increasing in the number of subsets that we get as we add elements. The ones we did yesterday with 2 elements to start with had 3 subsets. We jumped up to 3 today and got to 7. We did 4 and got 15. A 5 element set will have 32 subsets. They get bigger and bigger, faster and faster. Any questions on subsets? Like I said yesterday and the day before, or yesterday, chapter 1's a little all over the place, because with this we're going to talk about bounded and unbounded intervals, inequalities. Now, there's 2 types of intervals on a number line we can have. One of them's bounded, one of them's unbounded. The only difference between the 2, bounded says it's going to stop and end here. We got 2 definite endpoints. Unbounded says we have 1 endpoint and it continues on indefinitely in a single direction. We normally call those rays. A ray has a single endpoint and continues in one direction indefinitely. We kind of make sense of the 2, yes? Up to this point, you've already figured out I have a very dry sense of humor, hopefully. Is interacting with me at all. I actually had a friend in college named Ray. He was tired of me before the end of the first semester. At Christmas time, because I went to John Brown University, one of the guys' dormitories, they put up a big Christmas tree for the guys' dorm. And when I say big Christmas tree, this tree is 3 stories tall. The main dormitory has an interior atrium, 3 floors up. That thing touched the ceiling every year. And they decorated it. It was massive. Ray was helping decorate or help put the tree up. He was up on top pulling the rope. I saw him doing it and I yelled up to him, "Hey Ray, don't go too far. You can only go in one direction." Definition of a ray. He found those jokes less and less funny as the years went on. But a ray or an unbounded interval only goes in one direction. Bounded interval. We see all these words. Luckily, you do not have to write all those words. It's right there at the bottom of that page. Let A and B be 2 real numbers such that A is less than B. Then A and B are the endpoints of 4 different bounded intervals on the real number line. That seems like a whole lot of words to say something, yes? But the reason we do this and the reason we talk about it in this way is we want to describe any and all possible bounded intervals. All the first part saying, we have 2 numbers, any numbers. Doesn't matter what they are. It could be 4 and 7, 6 and 1500. We have 2 numbers. One of them is smaller than the other. That's really all the first sentence says. Then we want A and B to be the endpoints, the 2 places where it stops. For this here, and it's the set of all points between them. Now the first one that we have as an inequality is A is less than or equal to X is less than or equal to B. So we have all the points between it, and the 2 endpoints are included. So we fill them in. If an endpoint's included, it's filled in, it's shaded in. As an interval, this is where we have our parentheses and brackets. Bracket is included, parenthesis is not. So it's bracket A, comma, bracket B, whatever the values of A and B are. Our second type is that the endpoints are not included. A is less than X is less than B. Parentheses A, comma, B, parentheses. Those are 2 of the main types. Either both endpoints are included or they're not. But we could also have one of each. We could say that A is included, but B is not. A is less than or equal to X is less than B. So A would be filled in on the number line if we graphed it, and B would be an open circle. Or A is less than X is less than or equal to B. A is not included, but B is. So A would be an open circle if we graphed it, and B would be a closed. Questions on these here? Probably familiar, you've done these in Algebra 1, middle school, graph number lines, inequalities. Questions on bounded intervals? Now the other type we have is unbounded intervals. Let A be a real number. Each interval on the real number line shown below is called unbounded. With unbounded intervals, we have a single endpoint. We have a single number, that's just A. So we use these letters to define any and all. So just given a number on a number line, it's going to be greater or less than, or greater than or equal to, or less than or equal to. So our first one, X is greater than or equal to A. So we are saying all the points that are greater than or equal to A are included in this unbounded interval. In interval notation, we would do bracket A, comma, infinity parentheses. If you struggle with writing an infinity sign, y'all know an easy way to do it? Turn the paper sideways and write an 8. That's all it is. It's just an 8 sideways. Now with these here, infinity and negative infinity will always have a parenthesis. So even if we talk about the other few, let's bring all these up, it says no. X is less than or equal to A. X is less than A, so we're going to negative infinity because we're getting smaller and smaller, bigger and bigger negative numbers. Even negative infinity still has a parenthesis. Questions on any of this here? Now we do have the whole number line. There's really not an single inequality statement that satisfies this. What this would normally get, or how we would get this, is if we had two or statements where either one works and they were going towards each other. Because for inequalities, an or statement, as long as one is true, we satisfy the statement. Normally, when we see or statements or inequality statements, they're going away from each other. We have a gap in the middle of the number line when we graph it. Y'all remember doing some of those? They point in opposite directions, and what's in the middle is empty. That's most of them, but they can point towards each other, and we just fill the whole thing up. That seems kind of weird. Why would that work? It works the same way kind of in English, where you can have a hamburger or hot dog. So you can have one or the other, but or statements you can have both. Both is true. Both can be true with or statements. Questions on any of this so far? Now, some of the times I do get questions about why we put parentheses around infinity and not a bracket. Why can we not include infinity? It's for two main reasons. One, infinity is actually not a number. It's a concept. It's representing something that's massively big that is impossible to get to. Okay? Also, depending on, because since it is more of a concept, not an actual number, saying that infinity is bigger than others is true and false at the same time, depending on the context. Okay? Now, I will give you an example of this here that kind of may help you a little bit conceptualize this fact. You don't have to write anything that I'm about to write down. What we have in this concept, in this kind of brain thing, is going to be with our infinite hotel A. We have a hotel with infinite number of rooms. It extends out massively. There's infinite number of rooms in this hotel. We're going to say, for case in point, I am the desk clerk checking people in. We have every room full, and a customer comes in asking for a room. They want to be able to spend the night at the infinite hotel A. Being a good clerk, I want to try to help them get a room so they have a place to spend the night. So after thinking for a while, I come up with the idea. I phone up the person in room 1 and ask them if they would kindly move to room 2, asking the person in room 2 to move to room 3, 3 to 4, 4 to 5. Everybody's moving down one room. Infinitely. Yes? But what have I done? I've taken an infinite that was full and made it one bigger, because now room 1 is empty. That person can go into room 1. So even though we had infinite and it was full, I was able to get one more room in. So we were able to make it bigger. I didn't actually get to infinity because we just got to another one, yes? Kind of making sense? They've been doing well. Business has been booming. So right across the way, they built Infinite Hotel B. Unfortunately, it burned down. Luckily for us, everybody in Hotel Room B made it out just fine. However, everybody that was staying in Infinite Hotel B with its infinite number of rooms needs a place to stay. Now, we still have Hotel A. We need to see if we can get them to fit into our infinite hotel. So we're trying to fit an infinite number of people into an infinite number of rooms already full. After thinking for a while, we're going to do something a little interesting. I'm going to tell the person in room 1, okay, can I have you go to room 2? The person in room 2, I want you to go to room 4. The person in room 3, we're going to have them go to room 6. We're going to have the person in room 4 go to room 8. The person in room 5 is going to go to room 10. We're moving every single one to the next even number. Which means what? Every odd room is now empty. It's open, yes? The number of even numbers that we have is infinite. The number of odd number rooms we have is also infinite. So now we can take everybody from Hotel B and move them into Hotel A. You can get up to 10 hotels, 10 infinite hotels, and move them into one. The math on it gets a little bit crazier as we get higher and higher, especially how we're manipulating the numbers. But it is possible. This is why we can never get to infinity. We can keep making it bigger as we describe it. I also love thought experiments like this here. We understand it. It's kind of crazy we do, but we do. And it works. So, what we're going to do next is write each of these in interval notations. Interval notation? Interval, we're talking about parentheses and brackets. I know that this here, for some, is a challenge, doing the parentheses, brackets, actually being able to write these out. Yes? Especially if we're going straight from an inequality. Trying to figure out what do we have here, what is the points that we need, what are the points that we don't need. One way I've found that can sometimes help is graphing this. Actually looking at a graph. Does the problem ask us to graph it? No. But if graphing it helps you visually see it, do it. Because if we look at this here on a number line, it's saying that -2 is less than or equal.
Have your attention, please. Today at lunch, the FFA officers need to go get their trays and then go to the Ag building. That's during lunch hour. Thank you.
-2 is less than or equal to x is less than or equal to 3. So again, by our bounded intervals, A is going to be -2, B is 3. So on a graph, our 2 points that we have are -2 and 3. If we look at -2, we look at the inequality sign. If there's that equal sign, there's that line under the symbol, we know it's equal to, which means it's included, which means we take this point and shade it in. It's filled in, it's included. Then we're going to look at 3. It also has that equal sign. So that means it's also included. So we shade it in. Questions so far? Now we need to shade the line itself, yes? Where are we shading? In between the two. X is in the middle, so we shade in the middle. Now this kind of gives me a picture of what we're looking at. We're looking at all the numbers between -2 and 3, yes? We have 2 endpoints. Inequality said we had 2 endpoints, yes? So when we have 2 endpoints with intervals, we need both of those endpoints. -2 and 3. The order in which we listed, bigger number on the right, smaller number on the left. Bigger number on the left, bigger positive number on the right. We're going left to right, smallest to biggest. And especially when we have 2 endpoints, we need both of them, -2 and 3. Questions on how we got here? Now we need to determine if we use parentheses or brackets. If we look at the -3, was it included? Is it equal to it? Yes, so we would have a bracket. The 3, is it included? So it would be a bracket. Bracket, -2, comma 3, bracket. That's interval notation. With interval notation, there is no variable. We do not put an X or a variable, a letter in interval notation. Because interval notation is saying between -2 and 3, over this interval, over this time span, this is the numbers that are included. So especially when we see inequalities to interval notation, if we have two numbers and a letter in the middle, we're talking about bounded. Yes, there's exceptions, and the main exceptions if we have or, we have two intervals with or, a little more into that, but we're mainly looking at bounded and unbounded. We're not looking at our and or, mainly our or inequalities. Any questions on A? Let's look at B. So we will graph this so we can see it graphically and back to interval. How many endpoints do we have for B? 1, just -1, yes? So would that be a bounded interval? How many endpoints does bounded have? 2. So most likely we're going to have a number, we're going to have -1, but we'd also have to have what? Infinity or negative infinity. Because if we only have one endpoint, it's shooting off in one direction or the other. It's going to infinity or negative infinity. Now, when you graph for me or graph number lines for me, I do not need 0. I do not need scale. Here, the only number that we have on this number line is -1, yes? That's all I need. I don't need the rest of the number line. I don't need to know where it's related to 0 because the main information we need for this here is -1 and which direction it's going. We can put a circle at -1. So our statement is x is greater than -1. Is -1 included? Do we shade it in? There is no equal to sign. There's no line underneath that symbol. So that means it stays open. Now we need to figure out, do we shade to the left or to the right? We need to figure out which direction we're going. Are we going right or left? We're thinking to the right. If we're not sure, I always do every now and then just a test number. Let's say 0 is bigger than -1, yes? So I'm going to take it and plug it in for x. Is 0 bigger than -1? Yes, that makes a true statement, which means it should be included in the shaded region. So that's telling me I need to shade that way there. And yes, you can shade just like that. Now we could have also picked -2. Is -2 greater than -1? No, that's a bigger negative. It's smaller. So this is false. So that number should not be included in the shaded region. It is not a part of the solution. It is not a part of this expression. So it should not be in the shaded region. Kind of make sense? This works on the ACT. Given the following inequality or system inequality, the XY coordinate plane, which of the following shows the correct graph of this equation? Well, whichever graph is correct, the point x, even if it's given one number or a pair, an XY coordinate pair, should make the statement true, yes? So what you can do is pick one of the graphs, pick a point in the shaded region, plug it in. Plug that side into the calculator, see, do I get a true statement? Like 0 is greater than -1. If I do, it's included in the solution. It is a solution. However, if it's included in the graph, the choice, that answer choice, and it gives me a false statement like -2 is greater than -1, we know that's not a part of the solution. So that answer choice is now thrown out because that point can't be there. That answer choice says it is. And that's part of the reason we'll be doing some of the progress learning is to help y'all see some of these tricks where we don't actually have to graph a system or a two variable inequality. We can just get there. Questions on this so far? Are we ready for the next one? When we look at C, all right, I didn't even finish B. I'm getting ahead of myself. We graphed it, we just didn't write the interval, yes? Now, one of the nice things with intervals, we know we have an endpoint, yes? Which is -1. Now, our other quote-unquote endpoint, the direction it's approaching, is either infinity or negative infinity. It's going to be infinity. Their numbers are getting bigger, yes? Would infinity go to the left or to the right of our -1? To the right. It's bigger, yes? We're going to the right. So we'll put it to the right. Now, -1, is it included or not? If it's not included, it would be a parentheses. What would we do for infinity? Infinity always has in parentheses. Positive infinity or negative infinity will always have a parentheses. Always have a parentheses. So parentheses, -1, comma infinity, parentheses. All right, we finally answered B. Questions on B before we look at C and D? C does not have an inequality, it just has it already graphed, yes? As we look at this here, do we have one endpoint or two? Two, so that means it's bounded, yes? And it's kind of nice because it's telling me that the two endpoints are -3 and 4, yes? So that means we're going to need those two numbers. Which one's going on the left, which one's going on the right? That's one of the nice things about having it graphed, is it visually shows us -3 is on the left, 4 is on the right. So for interval, -3 is on the left, 4 is on the right. Now we just need to figure out if we're using parentheses or brackets. Brackets included, parentheses is not. As we look at -3, is it included? So it would be a bracket. Is 4 included? So it would be a, that's it. Questions on those here? We understanding? Kind of making sense? Let's look at one more. How many endpoints do we have? So that means that this is unbounded. And we will need that endpoint. We will need that 3. Is this going to positive infinity or negative infinity? Negative infinity. And it will have to be on the left. Positive infinity or negative infinity, we will need that parenthesis. Because 3 is filled in, it's included, we would have a bracket. Questions on this here? Questions on anything we've done so far? We good with this here? Ready for the next problem or problem type. So, the reason we go through this, because it seems kind of odd that we are talking about sets, different sets, and then we jump straight into inequalities. We need them. We need inequalities to start describing some sets of numbers. So, before we get there, if I was to say, you don't need to write any of this down, we wanted to write the set of real numbers greater than 1. So you don't have to write this part down, but we wanted to write the set of real numbers greater than 1. And up to this point, the main way we would do it is brace. What would our first number be? Or if we said greater than or equal to, let's add that. Well, we would say 1, yes? What would our next number be? I mean, we could do 2, but what about 1.1? Is it a real number? Well, yes, because our fractions, decimals are real numbers, yes? But wouldn't we also have 1.092736582? That would be after 1, yes? Wait, how many decimal numbers do we have that are after 1? A ton, yes? Is it feasible to actually write all the numbers greater than 1? No. Is there any way I can set up a pattern for this here? We could try. Because I could say just with fractions, I could have 1/2, 1/3, 1/4, 1/5, 1/6, or not 1/6. I did this last year too. 2/3, 4/3, 5/3, because we do have, or 2/3, and some of these here, we can make these fractions, because those are all between them, yes? Especially because 1 and 2/3, yeah, 1 and 2/3, 4/3 is 1 and, okay, that's actually, I keep trying to do this between 0 and 1, that's what I'm doing. So 1 and 1/2, 1 and 1/3, 1 and 1/4, 1 and 1/5, there we go. 1 and 1/6, 1 and 1/7, 1 and 1/8, 1 and 1/9, 1 and 1/10. But essentially I'm just putting 1 over every number there is, yes? Well, there's an infinite number of numbers. I just made the gap between 1 and 2 be infinite. There is no feasible way to do this. There is no way to write a pattern. So we're starting to see where I was saying yesterday, there are some sets where we are actually going to have a description for it. We can't just do a pattern. We can't just list them all out. Okay? Because for this here, if I wanted to write greater than or equal to 1, we're going to actually have to use these inequalities to describe these numbers. After chapter 1, you're not going to have to do this ever again. I like putting this in here because it's making us think critically and trying to problem solve and work our way into understanding how to describe this. For years, when we're doing this and talking about set builder notation, I included letters, I included numbers, I included symbols. However, I have decided it's easier to set it up this way: brace, triangle, bar, circle, so that we don't have any connection to what they are. There are 3 main things we put in here when we use set builder notation to describe these properties. The triangle. What is our group of numbers? Are we talking about the real numbers? Are we talking about the whole numbers, natural numbers, integers, rational, irrational? What is our number group that we're talking about? And the nice one is the real numbers. If we're talking about the real numbers, we just put X. Now, the nice thing is the bar, and it's funny because out of all 3 symbols, it's the only one that actually has words directly attached to it. Such that. When we see this bar in set notation, it means such that. We have this group of numbers such that it has this description. So if we looked at the previous one I just gave you, it'd be the set of all real numbers such that X is greater than 1. These are the type of numbers we're looking at. This is the description of them. questions on this here? Now, at this point, we're like, okay, I really don't see how this works or how we put it together, and that's fine. We haven't actually done anything with it yet. So we have a brace. We first put in, what are our number types? Such that the description. The downside is the description cannot be an interval. We cannot have parentheses, -1, comma infinity, parentheses. We can't have that. We actually have to have it in as an inequality. So let's actually see how this works. So we have some of these here. We already have them written out. I want to go through these here and give you what the graph looks like so we can kind of get a connection to what it's saying. So the first one in set builder notation, we have brace x bar. X is less than a. The way we would read this is the set of all real numbers x. So brace x bar, the set of all real numbers x. So any x, any real number that we can take and put in for x is what we're looking at. That's the number group. Such that x is less than a. Do we know what a is? No. A is just some point on the number line. A is a number. So we're saying that for any value of a, for any value of x, such that x is less than a. So if we said a is 4, we're saying that the value of x that we plug in there can be any real number. It's any number. It's just going to be less than 4. Okay? We kind of get this so far. I find the second one funny. Because again, brace x bar, we're saying this for the set of all real numbers x. For any value of x that we could possibly have, it's a real number, such that x is not equal to 3. So what could x be? Anything, yes? But it cannot be 3. Because at 3 we'd have a circle, yes? Where would we shade? We'd shade everything else. It can't be 3. We will finish this tomorrow.